Hey folks, Nathan here. Today we're going through the code of the FC-1 or the Flight Computer 1, the imaginatively named flight computer that's going to be flying on the first version of the Aquarion rocket. So I'm putting this video together because I imagine there's quite a few people out there who are looking at building their own flight computer, but might not know exactly where to start, especially on the code front. And I haven't seen too many videos out there that actually go step by step through the code of a flight computer and explain how to do it. So that's what we'll be doing today. Let's jump into it. First off, let's talk about what the flight computer is actually made from. So the brain is an Arduino Nano. It's light and it's cheap and it does everything we need it to do for a flight computer. We have a BMP280 module. This is a small barometer which is used to calculate our altitude. There's a lot of other modules that can do this as well, but once again the 280 is cheap and it does the job, and it also logs temperature, so if you want to start getting into sort of more sciencey stuff, like flying a rocket up to know how hot it is 100 meters in the air for example, then this chip will do all that. So that's the main reason I picked it over any other chip, was mostly just for that temperature reading, and it's got a pretty decent uncertainty. Next up we have a servo motor. This is what we use to deploy the parachute. If you're doing something with, say, ejection charges for your parachute deployment, then instead of a servo motor you're going to want to be using a pyro channel, and it's going to do pretty much the same thing. So wherever you see this servo, my servo in the code, just replace that with firing off your pyro channel. And here obviously we have servo.h, and that is our servo. We also have a LED. This is just so that we can know the state of the flight computer from the outside. So we don't want to have a wire plugged in to know what the computer thinks it should be doing. We want to be able to tell just at a glance what the computer's doing. And we have a button, which we just press the button and it will move us between various states. I'll explain what states are later, assuming you're just bare bones, haven't done any programming before. So we'll get to that. All right, let's start at line 1 and work our way down. So to begin with, we have our includes. We use the wire.h library. This does what's called I2C communication, and it's how we talk to our BMP280. We have the SPI.h library. This is another way of talking to the BMP280. We don't use it in this, we use the wire library, but it is still good to have in there because there may be dependencies that the 280 library has. Which brings us to the 280 library. We use the one from Adafruit from this just because they have really good example code that you can play around with. And then we have servo.h, which is what controls our servo. All very important. So these are essentially libraries that give you a whole bunch of extra code that you can reference so that you don't have to write out all the custom code for I2C communication or servo movement and all that sort of stuff. So we have variable declaration next. So we have the BMP variable, which is our BMP280. It does I2C communication, we can see from the comments here, and this here is where we need to wire it up to. So the SCL goes into A5 on the Arduino, and SDA goes into the A4. We have the servo, which is what controls our servo motor. We have a bunch of variables that we store here. We have the minimum and the maximum height that the rocket reaches. So we use this to calculate things like our apogee, knowing when we've launched, all that sort of thing. We have the current pressure. So I'll explain why this is needed later. It's not something you'd use in a lot of other flight computers, just because of the way that we're using it here, but there's a reason for it and I'll come to it soon. All right. We keep track of the current state. State machines are another one we're coming to shortly, but essentially there's 4 different states that the rocket can be in, and each one has different code that it runs. We need to define our pins, so our LED, which is a blue LED, which tells us our state, that is set to pin 7. Our button is set to pin 3, and our servo is plugged into pin 4. So these are just whereabouts on the Arduino that these things are attached. We have a couple of numbers here, the launched altitude variable. So this is, as it says here, what height does the rocket switch into launch state? So once the rocket reaches 5 meters above the pad, it's going to say, oh hey, I've launched, I'm going to move into the next state. As with this one here, apogee descent altitude. So once it gets 2 meters below the maximum height that it's calculated, then it assumes that it's in apogee and it's falling now. And that brings us to the setup. So setup is the first method that's going to be called when your Arduino turns on. So this is where you want to initialize any other variables that you need to, like setting your pins up, setting up your sensors correctly, and all that kind of thing. So what we're doing here, first off, we're starting a serial line. This is mainly just used for debugging on the computer because we don't want to have two different versions of the program, one with the serial, one without it, because then if we change something in the serial version, we might not change it in the live version, and then our rocket crashes. We don't want that. So even though the serial isn't being used in flight, it's easier to just start it, and maybe in the future we will plug something into it so we can log stuff, but for now it's not super important. Next up, we reset our values, which is setting our minimum and maximum altitudes. If we go down here to the reset values function, you can see that we set our minimum height to 100,000, which is an arbitrarily large number, and our maximum height to 0, which is a very small number. So these are done for comparison purposes. So if we say our maximum height, we calculate the height we're at. If it's higher than the current maximum height, then the new height is the maximum height. Same with the minimum height. We want to say if our height is smaller than the minimum, then the height that we're reading now is the new minimum. And in order for those comparisons to work on the very first variable that gets sent in, you need minimum to be high and maximum to be low, so that the first reading is always going to be both the minimum and the maximum, and you can work from there. All right, we define our pins. Our LED is going to be an output because we're just essentially firing electricity into it to make it light up. Our button is going to be an input pull-up. So just doing a button as a regular input typically leads to a lot of noise unless you do your own pull-up resistance. But because an Arduino Nano has resistance or pull-up resistors built into every pin, then we can just set the pin mode as pull-up and it'll do the rest for us. Basically, it just removes a lot of the noise for button pressing and makes sure we get more accurate readings. We turn off our light to begin with. Lets us know we're setting up. We go through here. If a serial's plugged in, then it'll send this text through so we can debug it on our computer. These are commented out. They're not needed anymore, but the altitude readout test is a function that essentially was there to test the altitude readout, which there's a separate video for in the description, but I can delete these. Okay. We want to initialize our BMP280. We've essentially created a function here for beginning the test. This doesn't actually do anything. I'm just going to clear these out. Ignore these here. They're irrelevant. So, read that as well. So, we want to call bmp.begin, and we feed in this case, 0x76. This is the I2C channel that the BMP280 is communicating on. So we want to say, look at this channel, find the BMP280. If you don't find it, then say, we couldn't find it. Ideally, we should put some kind of light flashing maybe in here so that we know that that's the exact issue as to why it's not starting up. And I might do that for the version 2 or FC2, but doesn't have to be done right now. All right. Now that our BMP280 is set up, we want to set our sampling rates. So most of these are just from the default Adafruit program. The one that I have changed definitely is the standby value. By default, this is going to be 200 or 400, which means that every 200 or 400 milliseconds, or between 2.5 and 5 times a second, you're going to be getting your pressure altitude readings. For a rocket, that's definitely on the slow side. You don't want to only be checking like 5 times a second what your altitude is. You want to ideally have a bit more control than that. So for that reason, I've just set it at 1, so 1,000 times a second in theory we should be getting an altitude reading. Alright, we say that our BMP 280 is initialized. Once again, this is a debug thing. And then for our servo, we attach the servo pin so it knows that this is where the servo is. And then we write 180 to it, which is the position in degrees on the servo motor that the parachute is locked in. Hey, we've explained the reset values, so that takes us to our loop and to state machines. So the first thing is the loop function. This is called anywhere from hundreds to thousands of times a second, depending on how complicated your code is, what delays are in there, and all that sort of thing. But the main thing you need to know is that loop is going to do just what it says it's going to loop. So it's going to run through this function, and then the next tick of the CPU, it's going to run through it again. And this is just going to keep going essentially forever. So what we have here for our rocket is a state machine. So what a state machine does is we essentially set up a bunch of predefined states. In this example, we have 4, as you can see. State 0, we're idle on the launch pad. State 1, the rocket's going up. State 2, the rocket's coming down, hopefully with a parachute. And state 3, we've asked for the readout. So we can swap between these states willy-nilly. You can add more states, you can have less states, you can have a state machine as complex or as simple as you like. But essentially all it does is say if we're in state X, then run code for state X. So we can see here, based on our state, if we're in state 0, run the idle state code. If we're in state 1, the launch state code, etc., etc. And that's essentially all a state machine is. It's just, I'm in this state, so do the things that this state says to do. So let's jump into state 0, our idle state. If we're in state 0, our LED pin is on, so that if there's a solid light, we know that it's in the idle state and everything's working right. If our rocket's sitting on the launch pad and it doesn't have this solid light on, we know something's wrong. Okay, next up is where we use our current pressure variable. This is something that is probably not advised to do for a normal rocket, but I'll explain what we do here and why we do it and what you probably should be doing. So what we're doing here is we're setting the current pressure variable, which is the pressure that we use for all of our altitude readings, and we're setting that to the current pressure at the launch site. We're then saying that our minimum height is going to be the altitude at that current pressure. So the way that the read altitude function works is that you're meant to put in the current pressure at sea level at your location. So if I was launching this rocket, say in the middle of Melbourne, I'd go into Google, I'd say, what is the current air pressure at sea level at the time that my rocket's launching? I'd put that into this code here where current pressure is, and then all of my heights would be above sea level. So it might say read altitude at my sea level is going to be I'm 1400 meters above sea level, for example. What we're doing here instead is we're saying to treat where the rocket is being launched from as sea level. So all the heights that we're going to get from this read altitude variable throughout the entire script are going to be relative to the launch site, which means that essentially we're saying, all right, the rocket is at sea level when it launches because we've set that here. And now any heights that we're going to get are just this height above sea level. For this particular script, it doesn't matter too much because it's a very simple flight computer and we're not doing anything too crazy. There may be reasons that you need to use the air pressure at sea level, particularly if you have any legal issues with flying things wherever you are. If those heights are calculated above sea level rather than above ground level, then I would very strongly advise that you essentially do what I said and look up what the pressure is at sea level at your location and put that into this script here. And that will give you an accurate reading above sea level, not above ground level, and that will let you moderate your height as required. But for this one, we're saying the launch site is sea level, and simple as that. That means that in theory our minimum height should be 0, because if the current pressure is sea level and our read altitude is the height above sea level, then that should just enter 0. Once that's done, we flash our LED to say, hey, the pressure's been set, well done, you did it, let's move on. Next up, this is where we move from the idle state to the launch state. The first thing we do here is we do a simple check. If the minimum height is greater than -1000, then we move on. So this is just in here as like a simple error check sort of thing. It means that the BMP 280 is working properly, essentially, because our minimum height should be 0. If it hasn't been set correctly, then it's going to be well below that value. Because if the current pressure hasn't been set, it'll be defaulted to 0, it'll be reading the altitude at a pressure of 0, and that's going to give us a very low number, if I remember correctly. So this here is basically just in there to say, hey, minimum height has been set, go for it. We could replace this with just a Boolean value of saying, has pressure been set, yes or no, and then say if pressure has been set, move on. But this is just a different way of doing it, essentially. So now we read our altitude, we take the minimum height away, which theoretically should always be 0, but maybe slightly higher or lower, just depending on the pressure variables with your BMP 280. We say if our height is greater than the launch altitude, which we set above as 5 meters. So once our rocket gets 5 meters above the ground, move to state 1. And what that will do is when we come back to the next loop, instead of being in state 0 and going to the idle state, we'll be in state 1, going to the launch state. So let's move into the launch state. Our rocket's launched, it's up in the air. What's it doing now? The first thing it's doing is making sure that its LED is turned off. Once again, this just lets us know the rocket's launched, so we have a nice visual reference. If it's on the launch pad and suddenly the light goes off, we can assume that it thinks that it's launched and it might be getting ready to deploy a parachute soon. We want to get our current height, which once again, we do a read altitude here, we take the minimum height away and that gives us our current height. If our height is greater than our max height, then set the new maximum height. Pretty simple stuff there. So, how do we know we've hit apogee, is what we want to know here. The way that we do this is by finding out if it's dropped significantly from its maximum height. Because there's going to be some fluctuation as it's going up, just because of wind and differences in air pressure and that sort of thing. So you will get some, like, as your rocket's going up, it might get some slight drops in altitude or some slight increases in altitude that are just sort of there as artifacts of the BMP 280 essentially. But we need to know, all right, if we've dropped this far, then we're probably going down again. And that's essentially what this says here. We take our maximum height minus our current height. That tells us what the difference is between those heights. And then if that difference is greater than 2, it means that our rocket has fallen down 2 meters from whatever its maximum height was, which means it's a pretty safe bet at that point that it's going down and it's hit its apogee already. Because we're deploying our parachutes at apogee, we want to write to our servo to go to position 0, which will deploy our parachute, and then we reset the servo back to its lock position, just so it's nice and convenient when it lands on the ground. Our state's gone to state 2, so we go back to our loop state, it'll loop around again, we hit state 2, we go to our descent state, which is here. For this flight computer, the descent state doesn't really do much. We don't have anything that detects when the rocket's actually landed, because there's nothing currently that will benefit from that, essentially. Because the readout for this is done by LED, we don't want it to start reading out its altitude the moment it lands, because we might miss it. So if you've got an SD card attached or a flash chip attached or something like that, this is the point when you're going to want to start writing your data to that. And I'll explain a bit on how you do that. But for this one here, all we're doing is turning off our light, and then if the button gets pressed on our circuit, then start reading out the altitude. So the way that you might do this, if you've got, say, an SD card attached, for example, you could just have it button based as well. So if you don't want to detect when it's landed, you just say, all right, I hit the button, now start saving all the data out. It's a very easy way of doing it. You don't have to worry too much about when it's landed or any of that calculation, because in theory, if the button's been pressed, you're the one that's pressed it because the rocket's landed. The way that you do a detection of landing, there's a bunch of different ways to do it, but probably the easiest one would be check every half second to a second your current altitude. If that altitude is staying the same for a few seconds, then it's a pretty good chance that you've landed at that point. All right, then we move to state 3, which is our altitude readout. I have a separate video on this, which I'm going to link in the description, that explains how exactly this altitude readout is done. But this here is the part where you'd replace this script with your preferred readout method, whether it be single LED like I've done here, or SD card, flash chip, radio module, Bluetooth, whatever you've set up to say, all right, tell me the altitude and any other data, this is where you'd put it. Once the readout's done, we go back to our idle state and we reset our values again, so our minimum and maximum heights reset to what they were. And we find ourselves back here in our idle state. And that's our entire flight computer. It's 230 lines of code. About 80 of them are this LED readout, so really it's about 150 lines of code, if that. So yeah, nice and simple. I hope that this has helped anyone out there who's looking to build their own flight computer. If you're not doing exactly this, it should at least give you a pretty good guide, I think. So yeah, that's it for this video. I'll catch you later.